Machine learning is an important enabler for optimizing, securing, and managing mobile networks. For 5G, the 3GPP has defined a network data analytics framework that various functions in the network can make use of. This leads to increased collection and processing of data from network functions and mobile phones, which in turn may leak sensitive information about end users. While the 5G Network Data Analytics Framework contains mechanisms to protect the privacy of end users, this project was set up to study ways to further improve protection via other approaches. In traditional machine learning, data is collected and sent to a central location where a machine learning model is trained. This data may contain sensitive information. Collecting it in a single point increases the risk of that point being attacked. One approach to reduce the risk is to use federated learning. In federated learning, machine learning models are trained locally in the clients where data is collected, avoiding a central server having access to their raw data. The local model updates are then sent to a central parameter server that merges them into an update of the global machine learning model. The global model is then transferred back to the clients, who can use it for predictions and further training. Information about the data may still leak through the updates themselves. To prevent the parameter server from getting access to the updates, one can employ a multi-party computation protocol. Using secret sharing, the clients exchange masks. The clients then use the masks to hide their local updates before sending them to the parameter server. The way the masks are constructed and shared enables the parameter server to aggregate the hidden local updates into a new global model without being able to unmask any of them. Masks come in pairs, one positive and one negative part. When combined, these parts cancel each other out. Here, masks are represented by the colored balls. Two masks in the same pair have the same color. Clients add several masks to their local updates. Once the parameter server receives all masked local updates, it combines them into a single aggregate. As can be seen, during the process, each mask is combined with its paired mask of the same color. And when they are combined, they cancel out. When all masks are canceled out, the result is the unmasked aggregate. In this project, we integrated federated learning in the 5G data analytics framework and added a multi-party computation protocol to protect the local model updates. We constructed the scheme to fit with the 3GPP 5G functional architecture and followed its protocol and architectural design principles. It also makes use of the existing operator-controlled PKI and so reduces the need for additional key management, which could be complex and costly. In particular, we integrated the protocols in the Service-Based Architecture, SBA. This is a new framework introduced in 5G for harmonizing the components of the core network protocol architecture. It is based on modern cloud communication patterns. The 5G Network Data Analytics Framework is built on SBA principles. It enables service consumers to request or subscribe to events occurring at service-producing functions. The framework also contains a Network Data Analytics function. This function collects data and offers predictions and analytics services to service consumers in SBA. Service consumers then use this information to optimize network efficiency and reduce resource consumption. Even though we designed our protection scheme in the context of 5G, the general structure can be reused in other systems. We outline how our work can be fitted into use cases in the WARA-PS research arena, for example, where object detection models are trained locally in UAVs.